In this lesson, we're going to learn some more ways we can determine if a series converges or diverges as we let the terms of the sequence go to infinity. The first is a pretty general test, and it can work on a lot of different series, but it's one of the slowest to work with because you often do have to do sometimes pretty difficult integration in order to get it work. But it is called the integral test, and it says here, let a sub n be a sequence of positive terms. So we have entirely positive terms within our sequence. And suppose that a sub n is equal to f of n, so we just have a function which represents the values of the individual terms of the sequence. And f is a continuous, positive, and decreasing function of x for all x greater than or equal to some value n, where n is a positive integer. Okay, so there's a lot of constraints here, but effectively, we generally have a function within our sequence already. So, and that usually suffices. Really, we just want to make sure that function that's given, which we call f sub n, is continuous. So there's no jumps, breaks, asymptotes, whatnot. Entirely positive, so it doesn't go into the negative values of the the y values. And decreasing. All right, so continuous, positive, and decreasing. That's the most important part. All right, now the way this works is that the series from n equals whatever that starting value is to positive infinity, and the integral of that particular function, and it's switched from n to x, but that's okay, it's still the same concept. But if you can integrate that function from that starting value to positive infinity, these two results will either both converge or both diverge. So the idea is you will do the integral, this infinite integral, and if it converges, then that tells you that the series converges, and if it diverges, then that tells you that the series also diverges. It doesn't tell you what it converges or diverges to, which I'll show you through an example, but it does tell you that it converges or diverges, which is a pretty important result. Now, there's a proof that I could go through, but I don't know that the proof is really the most important thing to understand here. I'm just going to give you a sketch of an idea as to how the integral test works here. And I think you'll agree that it's pretty straightforward once you see it. So let me pull up an app here. All right, so I have here the graph of the function 1 over x on the interval from 0 to about 7. Now normally, of course, we would be integrating on an infinite scale, but we can't use infinity in the computer, so we'll just approximate a little bit. So here's the thing. The integral under the curve would look like this. And so it's the area starting from our lower bound up to our upper bound. Right now, as I let that area increase, the value of the integral is either going to converge to some number or it's going to diverge to to infinity. Now, here's the idea. The reason that tells me what's going on with the series is because the series is the sum of the individual integer values along this interval. So if I plug in 1 to my function, I would get 1. If I plug in 2, I would get 0.5. So 1 plus 0.5 gives me a total value of 1.5 plus the next point, plus the value at the next point, and so forth. So that's what we're adding together to get our series. Now, another way to think about that is using approximating rectangles. Okay, so if I use approximating rectangles, And let me see if I can get them to where they're integer values here. So if I make that, whoops, there we go, perfect. So the value of this rectangle, the area of it that is, would be found by taking the width of the rectangle, which I've set to 1 each time, times its height. And so the height is dependent upon the curve. So this is basically evaluating the first point in the sequence would give me the area of this rectangle. The second point in the sequence would give me the area of this rectangle, and so forth. So if we add up these rectangles, we're effectively coming up with a value that is the series. Now, here's the thing. If you'll notice, all of these rectangles are over approximations. And so what that means is if the integral, so just this part, does not converge, if this area doesn't converge enough for, or sorry, it doesn't go to 0 fast enough for the area to converge, then a sum that's going to go slower to 0 than that is also going to diverge. So they would diverge together. Okay, now here's the other thing about this. Let's suppose that this is going to 0 fast enough to converge. Well, using left endpoint rectangles is not the only way to get the approximate area under a curve. We could use right endpoint rectangles. And so that would look like this. So all of these rectangles would be smaller in value than the integral. So if the integral were converging, then all these right endpoint rectangles would sum up to something smaller than that and would also converge. Now, the way that we come up with the integral is by allowing more and more rectangles to fit under the curve until we add them all together. So what happens is the left endpoint approximation and the right endpoint approximation end up, equaling each other. So the idea is that if the integral converges, then that tells me that there's enough information to decide that the series converges. If the integral diverges, then that's enough information to tell me that the series diverges. And that's enough of the proof for you to get an idea of how this works. Okay, so let's take a look at an example problem. So the first example I have here, the series from n equals 1 to infinity of 1 over n cubed. Okay, so to determine if this converges or diverges, here's what I'm going to do. I'm going to apply the integral test, and you always want to state what test you're using, and then you need the evidence for the test. So the integral test says to evaluate the integral from whatever that starting point is to infinity of your series or your sequence terms. And you can leave this in dn, or you can change it to x dx. It doesn't really make a lot of difference. But because this is an improper integral, we do need to change this into a limit. So I will make this the limit as, let's say, t goes to infinity of the integral from 1 to t, and I'll go ahead and change this into n to the negative third dn. Okay, so next up I will evaluate my integral here. So using the power rule, I would add 1 to negative 3, so that's n to the negative second over negative 2, and that's evaluated from 1 to t. The 1/2 multiplier can come out front, so negative 1/2 times the limit as t goes to infinity. N to the negative second would be 1 over n squared, so let's call this 1 over t squared minus 1 over 1 squared, which would be 1. All right, now, as we let t go to infinity, the value of this first fraction here will go to 0. So essentially, I have negative 1/2 times negative 1, which is positive 1/2. And that's a real number. So that tells me that the original series converges. So the result is that this original series converges. Now, it doesn't tell me what that converges to. And let me show you exactly why that is. So here are the terms of that sequence. So the sequence 1 over n cubed, these are the individual terms. Now, we're not looking at what the terms of the sequence are doing. They're going to 0. We're looking at the sum of those terms. So that's going to be the infinite series. So if I add up these terms, this is the sum that I'm reaching. Now the value of the integral, so this function here that passes through my sequence terms, the integral from here, from 1 to infinity, resulted in 1/2. Well, the total sum of the first point is 1. That's already bigger than 1/2. So clearly these things aren't equal to one another. The test doesn't tell us what that value reaches, but if we estimate it just by this horizontal line, it looks like it's going to about 1.2, but that's hard to say for certain. We'd have to do some other testing in order to determine that. So just don't get into the habit of thinking that the integral test tells you what it converges to. It only tells you that it converges, or if the integral goes to infinity, that it diverges. All right, let's look at our next example. And here we want to use the integral test to determine whether this next series converges or diverges. So I have the series from 1 to infinity of 1 over the square root of 2n minus 1. All right, so we will state that we are using the integral test. All right, which tells us to take the integral from 1 to infinity of this sequence. All right, so I need to change that, of course, into an infinite limit. So 1 to t. And another thing that might be helpful here is to use u substitution when integrating. So I could go ahead and really get that started and say, I'm going to let u be the part underneath the radical, so that du is 2dn. So I have 1/2 du is equal to dn. So that this would become 1/2 1 over the square root of u du. Although my endpoints are not quite correct any longer, because the thing is, the original endpoints were in terms of the variable n. Now I have endpoints in terms of the variable u, and so these aren't matching. It's a very easy transformation. Just use the transformation function you have here. So u evaluated at 1, the lower endpoint, would be 2 times 1 minus 1, which looks like it would also be 1. So that's actually fine. And then u evaluated at the upper point, which is changed to t, is going to be 2 times t minus 1. All right, so it'll just be that function instead. So this will become 2t minus 1. Okay, so So I'll pull the 1/2 out, limit as t goes to positive infinity, and write this from 1 to 2t minus 1 and u to the negative 1/2 du. When I integrate that, I'll add 1 to the 1/2, so that'll be to the positive 1/2, so u to the positive 1/2 over 1/2 between 1 to 2t minus 1. The 1/2 can come out as a multiplier, but it'll actually cancel with the 1/2 that's on the outside because it's dividing. So those will cancel. That's fine. And then I have the limit as t goes to infinity of, I'll have the square root of 2t minus 1 minus the square root of 1, which is just 1. And let's see what happens here. So as we let t go to infinity, the value of this square root is going to also go to infinity. And if the value of that square root goes to infinity, then that pulls the overall limit to infinity. So what that means is this other series, the original, diverges by the integral test.